me today. I'm really excited to be here. That was a super exciting presentation about straw and cellulose, and I'll be touching a bit on carbon in this presentation as well, but as you can see from the title, which I've called wet wood, we're going to be talking more about moisture today in mass timber. So just to get started, and I know I'm preaching to the choir here, but we're obviously very aware of the impacts of climate change. A lot of these images are from just the past year alone, smoke outside the city, flooding, and then also the emergence of extreme heat cooling centers, and all just kind of the infrastructure that's going into that. So it's estimated that approximately 40% of global energy is currently devoted to buildings and construction, and in Toronto that number is actually higher at around 58% of our building industry is contributing to our emissions as a city. And so these statistics aren't something we can really be ignoring anymore. And so it's estimated that we will build 230 billion meters squared of new construction and major renovations worldwide between now and 2060. And so just to put that in perspective, that's like building an entire Manhattan every month for 40 years. So with that, we need to be considering what we're building with. And so, I'm not going to stand here and kind of tell you that mass timber is the only answer, but trees, especially in the last 5-10 years, have definitely kind of emerged as like a beacon of hope in all of this, among other low carbon materials, as we've just seen. And so when we think about wood, there's still a carbon positivity in terms of the manufacturing, but that raw lumber, as was just explained in the forest, sequesters carbon throughout its life. So if we're comparing a structural material compared to concrete or steel, we still know that wood is going to be orders of magnitude less in terms of its carbon. And you can see that the impact in millions of tons per year is going to go down as we're using timber more and more. So we know a tree can absorb over 48 pounds of carbon dioxide a year, which means that in 40 years, we know that a tree will have sequestered 1 ton of CO2 equivalent in 40 years, which is approximately a 6,000 kilometer drive, 6 months of powering a home, or 11 years of powering a fridge. To put that into perspective, one of my students put it in terms of garbage bags during their presentation last week, so that was pretty funny. But as demand for more sustainable construction materials and methods increases, mass timber is really shaping the future of low carbon construction in Canada, especially when we start thinking about Part 3 construction. So one of the areas of research that's kind of limited at this point, obviously we know we had to be researching fire so that we could be constructing above the 6-story limit of the MBC that was prior to 2020, but we don't have old mass timber buildings yet to be thinking about what types of issues might arise from exposure to moisture on site. And so this is where this research really comes into play, and I did have this, there's Greg, video that was supposed to be playing while I was talking. Anyways. And so this is the first case study I'll be looking at is Toronto and Region Conservation Authority's new headquarters facility that's being constructed right now. It's nearing completion up near Black Creek Pioneer Village, near York University. And so you can see here in the superstructure actually, even the cores are CLT, which is also a bit abnormal in North America at this point. Usually they're using a hybrid structure of concrete cores with CLT superstructure. But you can see throughout the kind of much longer exposure period than they were anticipating, to be diplomatic, they were running into a lot of moisture issues. So that's kind of, this is just on the floor assemblies, but my research will be focusing on the roof assemblies, but you can see they're trying to, talking about how are we going to get rid of this water? Anyway, so they're squeegeeing it down the holes, and this leads to kind of a domino effect of issues of like trying to protect the wood while it's on site. This is actually kind of a skewed image of the roof membrane, which was applied to the wet wood and effectively got destroyed within couple days and was starting to lift. You can see moisture kind of pooling into the floor plenum through different orifices of the building, and just a lot of issues that you don't really need to be considering as much when you're thinking about concrete or steel buildings. And so, oh yeah, there's me installing sensors with a giant drill bit. that's the end of the bit, if you can't see it. So that was, our sensors go right through, and I'll show a bit more on that in a second. The sensors under the floor plenum there go into the wall, and then we have some that are more exposed in the ceiling as well. And so just to continue that domino effect, what ended up happening on this site was they actually had to tent the entire structure and blow air into it for, it was like 5 or 6 months, I think, to dry out the wood before they could apply a whole new membrane system. So definitely something you want to be considering and avoiding when on site. And so our research, just before I get into the basics here, looks a lot at kind of a few different moisture mitigation strategies that are being proposed in the CLT Handbook of Practice and other resources. But there isn't really consistent moisture mitigation plans yet, even in Ontario, amongst the manufacturers we have here of mass timber. So just a few quick questions as a primer before I kind of get into the main meat of the research. How does wood get wet and store moisture? Well, at a microscopic level, wood is hygroscopic, so that means it has all these little holes that are called lumens that are storing wood. And this softwood is the type of wood that is typically used for mass timber products. You can see it's a bit more homogeneous, and so for me that means I can predict how water is going to move through this type of wood more easily than this type of wood. Anyways, that's my own thing. But we're talking about bulk water and water vapor when we're talking about moisture content. And so why does wet wood matter? Basically, according to the large majority of research to date, the risk of mold kind of starts at around 15% moisture content in wood, and that like varies depending on the product and the species, but that's kind of rule of thumb. It's also what the PRG 320 standard states that wood should be in service in Canada and the US. And then the risk of decay, so risk of mold is what's going to affect occupant health in the building, and risk of decay is what's going to start to affect the actual structural integrity of the material. And the risk of decay is a little looser in terms of what I could find in current literature, showing above 20% for sure, 22% range, we start to see that. And so we were getting off the chart ratings at the TRCA in their roof, especially above 30%, which is actually kind of beyond the limits of what even the sensor can measure. So above 30%, we're like, okay, it's super wet, I don't know. And so here's like, where do we typically see wet wood on site? We see it coming primarily through the end grain of the wood, so parallel to the wood grain itself is where moisture is coming faster into the material. So at any kind of cracks and joints, you know, mass timber isn't a perfect material, so this is quite common. And then these little, you know, what do they call them? Surface splines, but they're effectively little bathtubs on the surface of the roof where, you know, water comes in, sits in here, and then they put a little piece of plywood that gets screwed in, and that plywood just gets super soaked and holds the moisture against the end grain of that area of wood. So that's where we were seeing the highest values. And so this is a wall assembly, but I thought a great diagram showing also the impact of different types of membranes being applied. So if you're looking at a permeable membrane, we know that we can dry out through that membrane, whereas if you're gonna slap an impermeable membrane on wet wood, it's going to have a much harder time drying out, and that dry out period is much longer in wood than kind of we are used to considering when we're slapping these products onto buildings. One other aspect that people are looking at is actually the integration of this air cavity into the roof assembly, so it's a bit unusual, and they're looking at whether or not that would be mechanically vented. In my research, I'll show you, we just actually put an air cavity there and didn't even vent it, just to see if that would improve kind of the capacity for the wood to dry out. And so how we were kind of monitoring this is using this pin probe moisture content sensor. So basically these probes are insulated to a point, and that takes the resistance measurement between the two probes to tell us the moisture content at specific depths throughout the CLT. And so these are, for example, in a wall assembly, we get or roof assembly here, we can get several different depths throughout the CLT, and that's one of the installed sensors in our panels. And then here's a few images of the sensors installed on site. That's my colleague Yash up on a ladder with his laptop. I don't know, doing something there. And then we're showing part of what the TRCA is doing too is really trying to encourage tours of the facility. And so part of that is going to be our research. We're going to install some signage and probably QR codes that go with this so you can access the data. It's public. Just some more bathtub images here of those splines really kind of getting destroyed, and then you can see the aesthetic damage that it's doing in here. And so we strategically placed these where we were seeing a lot of this to measure kind of what was actually going on. And so we were doing sensors, moisture content probes in the kind of interior layer of wood, the center layer of wood, and then the most exterior layer of wood, so that we could get kind of a distribution profile of that moisture movement. And so I kind of already introduced these already, but the three main variables that we decided to test with the roof assemblies was whether or not the assembly was protected on site, so a pre-applied membrane before it gets exposed to high moisture conditions, what type of vapor retarder is used, and then whether or not there's an air cavity included. And so in order to kind of compare apples to apples, we decided to construct this test HUD. It's actually just over at our, we call it the B-top site. It's at Dundas and Mutual. And there's 8 different panels looking at that there. So this is us prepping the panels. And this is, you can see the little spline. And then so we basically sealed the edges of all the panels so that we could kind of assume that that result was continuous. And then this is all of our sensors getting installed on these panels. And then before, for 2 months, they just kind of sat on the roof of this facility we have on the B-top site. And then for the 2 months directly prior to installation in the test hut, we super soaked them. An inundation test, we call it in building science, but it's a bathtub, on top of these panels. And you can see some are protected and some are unprotected, and some are protected with permeable membranes and some are protected with impermeable membranes. And we decided to start building the hut in a snowstorm in October. And then this was just, as I was going through the photos, I found this kind of like lovely compilation of just Greg's face. Anyways, and so we're putting the panels here. Yash is working on some different like wall tests, and then you can see the roof test panels up there. But the most important part was what was happening on top of the roof. So you can see the 4 unprotected panels, and then we have impermeable and permeable vapor retarders on them as well. And then you can see the air cavity strapping going in to those ones, as well as the splines. Those are the splines. And you can just kind of see how the sensors got installed. So these are the typical panel sensors, and these spline sensors kind of take the rating of moisture in the spline itself and then directly below it. So we can kind of see how much is moving from that plywood bathtub into the CLT. And that's just a view from below. Now, this is really tiny. I know it's tiny, but I'm kind of at the phase of data analysis right now where I do sort of like squint when I look at it, because I'm trying to just see like big picture relationships at the moment. And so here, if you probably actually don't need to squint because it's already squinty. But the protected versus unprotected, you can see in the unprotected case, you have much higher peak moisture contents, which is honestly as predicted. And so that just really extends the dry out period. And so the next kind of phase we'll be looking at kind of how long we're in a mold risk zone, basically. Impermeable versus permeable. You can see again, impermeable especially. So these are just the different kind of layers. I should have mentioned that. This is the interior wood layer, center wood layer, and then exterior wood layer. So you can see especially on the exterior wood layer, what happens is the wood starts to dry out this way. And so that layer actually gets kind of loaded against the impermeable membrane and takes even longer to dry out. And then whether or not you're including an air cavity or not. So you can see where there's no air cavity, that's where we're seeing a lot higher moisture content in that most exterior wood layer. This one's quite squinty, but we had some, I don't know, the sensors were doing some weird things here, but the one kind of graph that looks really quite clear to me is this one, and that's, so this is for the splines in particular, and this is including an air cavity. So you can see that we can predict the dry out of those kind of spline conditions when you include an air cavity above them quite well. And it's like, this timeline is probably about a month before it starts kind of drying out. So, to summarize where I'm at currently, CLT enclosure assemblies that are subject to high levels of moisture for extended periods of time are at serious risk of mold growth, which could potentially contribute to health impacts and potential risk of rot structural impacts. Those we're seeing less of. Above that 20-21%, that's quite wet. So it's really, we're in kind of more of the mold growth range. Unprotected CLT is subject to much higher peak moisture contents and takes much longer to dry out after enclosure, even with the presence of an air cavity. So that higher initial moisture content showed panels in mold risk zones for a few months before they started to dry out. And we were only ever able to get our panels up to about 22-23% compared to the TRCA, which actually had them much higher. So I don't have that data yet from the TRCA, but I'm collecting it now. Protecting CLT on site with a permeable membrane mitigates moisture uptake during construction and promotes faster dry out after CLT enclosure. In CLT panels, including an air cavity had a similar effect on dry out rate as the use of a permeable membrane. So, yeah, if you're using a permeable membrane, it's going to dry out faster, which was expected, but the presence of an air cavity kind of was the same relative to that. In CLT splines, including an air cavity, increased dry out rate and reduced mold risk zone, period. And then finally, based on these findings, it's recommended that timber structures be protected as soon as possible from moisture during construction. That feels like an obvious thing, but we can see the direct kind of benefits of that. And then that air cavities be considered if using roof surface spline connections. So we didn't find as much benefit to the air cavities in the panels themselves, but depending on how those panels are coming together, it's something that you might want to consider. And so just kind of moving forward, this is Greg's contraption. He's soaking the panels right now. So currently it's raining in the test hut. Because we're trying to kind of mimic a roof leak scenario and see how fast the panels dry out in that case. I know at TRCA they do have a leak detection system, but it's not the like expansive one. It's sort of in points. And then further to that, like I mentioned at the beginning, you know, we don't have 20-year-old mass timber buildings yet to be thinking about. So the point of this research also was to collect data that would allow us to simulate longer term conditions so we can kind of predict the moisture fluctuations and predict if there is a roof leak. Okay, if your wood gets to, let's say, 22-23%, how long is that going to take to dry out? How long are you in any kind of mold risk or a decay risk zone? So to be continued, but this is where we're at. And 30 seconds, so thank you so much.